everyone. In this presentation, I will be discussing on how to derive the relationship between line as well as phase quantities and the expression for power for balanced three-phase star-connected load. As we have already seen in the previous presentation, this is how we are going to represent a three-phase star-connected system. So here we are having three distinct notations in terms of R, Y as well as B. So if I want to represent a star connection, I'm having a representation in the form of just like inductor. So you are having a phase over here, which is nothing but an R phase represented in red color, and B represented in blue color, and Y phase represented in yellow color. So here if you see the connection, how we are going to have the connection for each and every individual phase. So a particular phase, if I consider it as an example of an R phase, it is having two distinct leads. So the top lead as well as the bottom lead over here. So one of the lead will be connected to a common point and another lead will be connected to the line wire. So these red, yellow and blue color lines, what you can see over here, are called as line wires, R, Y as well as B. So each and every individual phase, what you are going to see, that is the red color representation, yellow as well as blue color representation over here. One end of them will be connected to the line wire. It may be R for the red color, Y for yellow color, B for blue color. So another end of all these things will be connected to a common point, which we call it as a neutral point. So if I want to represent it in terms of ER, EY and EB, so here if you see ER, EY and EB will be called as a phase voltage, which is represented in terms of ER, EY and EB for each and every individual color, what you can see over here. Whereas if you see this particular ERY, EYB and EBR, those are nothing but the voltages which we are going to represent in between two distinct lines. So if I want to represent the line voltage between the line R as well as Y, it is represented as ERY. And if I want to represent the voltage or the value E by B in between the line Y as well as B, it is represented in terms of E by B. Similarly, in terms of in terms of R as well as in terms of B line, it is represented as voltage EBR. So whatever the voltages ER, EY and EB you can see over here, those are represented as a phase voltage. Phase voltage is nothing but it is an voltage which is corresponding to a particular voltage with reference to the neutral point or a common point N over here, and ERY, EYB and EBR represent the voltage in between each and every individual lines, and hence it is called as a line voltage. So this is how you are going to draw the phasor diagram, or it is called as a vector diagram for a star connected system. So we have already studied that each and every individual variable in terms of ER, EY and EB, all of them are separated by an angle of 120 degree. So here you can see ER to EY, EB, everything will be represented in terms of a 120 degree angle. So we have seen what are these representations in terms of ERY, EYB and EBR. And what is this ER, EY and EB? So from the previous diagram, it is clear that ERY, EYB and EBR will be called as a line voltage. ER, EY and EB will be called as a phase voltage. So how to draw this particular vector diagram or a phasor diagram? So ERY, that is the line voltage in between the line R as well as Y, is represented in terms of an equation ER minus EY. Similarly, EYB is represented as EY minus EB. EBR is represented as EB minus ER. So first we are supposed to draw the lines, the colored lines, what you can see over here, that is ER represented in terms of a red color and EY as a yellow color line, and EB in terms of a blue color line. So those three colored lines, each of them is separated by an angle of 120 degrees. So in between blue line and red line it is 120 degree, in between red and yellow line it is 120 degree, in between yellow and blue line it is once again 120 degrees. So once you represent these ER, EY and EB notations, next thing we have to concentrate upon the expression. So what is ERY? ERY is ER minus EY. EY is nothing but this yellow color line. So I want minus EY in this particular expression. So I am supposed to draw a line opposite to that yellow color line. So opposite direction of this yellow line is towards the top portion. So if this becomes EY, obviously the opposite line should be represented in terms of negation, that is minus EY. So I am having ER line as it is because it is positive in this expression. So ER line minus EY will give us a line voltage ERY. So in between that, if I take a line, it is going to represent a line voltage ERY. So center of ER as well as minus EY. So since this particular angle will be 120 degrees, that is in between ER and EB, so obviously it is taken at the center, so this much angle will be half of 120, that is 60 degree, and again this ERY is taken in between minus EY as well as ER, so it is half of 60 degrees, so it is 30 degree. Same concept I can apply over all the remaining vector or phasor representation. So I got the ERY, then simply join a line through minus EY to ERY, ER to ERY. So this gives us the expression ERY is equal to ER minus EY. Next is EYB is equal to EY minus EB. EYB is a line voltage in between the line Y as well as B, whereas EY as well as EB are the phase voltages of Y as well as B. So EY is positive over here and EB is negative. So EY we have already represented it in terms of a yellow color line, and I want minus EB. So EB is already represented. Minus EB means it is exactly the opposite direction of the EB. So it will be bottom. So if this is EB, the next opposite direction representation will be in terms of minus EB. EYB is equal to EY minus EB. I want EYB, so draw a center line which is going to represent EYB and join from EY to EYB and minus EB to EYB. Just like this particular first case, I can represent the EYB equation. Last it is EBR. EBR is given in terms of equation EB minus ER. So here minus value is for the value of ER. So ER is already written in the red color line. So opposite direction, if I draw a line or take a line, it is going to represent me the negation or the negative value, which is minus ER. EB is already drawn over here, blue colored line. So in between EB and minus ER, I will be obtaining the equation for EBR. So this is the central line what you are going to draw, and it is going to give us a value of EBR line voltage. That is the voltage in between the line B as well as R. So this is how you are going to join from EB to EBR and minus ER to EBR in order to get this particular third equation. So this completes your phasor or the vector representation of a star connected system. Next is we want to find out what is the relationship between the line voltage as well as the phase voltage. So here ERY is the line voltage, ER and EY is nothing but the phase voltage. So this is the equation. So in order to link between the line voltage as well as phase voltage, we are going to follow a particular law which we call it as a parallelogram law of vectors. So by that particular law, it is stated that whenever I am having the equation of this kind, that is EAB, that is voltage in between A and B, is equal to, it is represented in terms of an equation EA square plus EB square plus 2 EA EB cos phi. So this is the general representation of parallelogram law of vectors. So similarly, I am going to apply this particular concept in order to have the equation for a line voltage, that is in terms of ERY. So instead of AB, I am having it as RY, and A is represented in terms of R and B is represented in terms of Y. So it is ER square plus EY square plus 2 ER EY cos phi, where this phi represents the angle in between the voltage, that is ER as well as EY. So EY, in the sense it is minus EY. So in between ER and minus EY, I am having an angle of 60 degrees. So instead of phi, I am going to substitute it as cos 60 degrees. So what is ERY? It is square root of ER square, as I have already shown you in the first slide, where ER, EY and EB will be the phase voltage. So I can represent the value of ER, or if I am having in my equation EY, or I am having EB in my equation. So all these ER, EY and EB are representing the phase voltages. So they can be equated as equal to phase voltage, that is EP. The same thing I have used over here in the derivation. Instead of ER, I am substituting it as EP. So ER square has become EP square, plus EY square has once again become EP square, plus 2 ER EY is written as plus 2 EP. EP cos phi is nothing but cos 60 degrees. So if you just simplify this particular equation, you will be getting it as EP square plus 2 EP square. EP multiplied by EP, it is EP square, multiplied with cos 60 degrees, which is nothing but half. I have written it as 0.5 under the square root. So if you further simplify this equation, 2 into 0.5 will be 1. So it is 3 times EP square. So it is square root of 3 EP square. So what is ERY? So ERY, EYB as well as EBR, all these are the line voltages. So instead of representing it as ERY or EYB or EBR, I can represent it as EL, which is nothing but a line voltage. So that particular value of line voltage will become equal to root 3 EP. So here I can state that the relationship between the line voltage as well as the phase voltage in case of star connected system, it is EL is equal to root 3 times EP. So only for star connection this particular equation holds good. For delta connection we will be deriving it separately, which is not going to yield the same equation. So now from the previous derivation, I've got the value of the relationship between line voltage as well as phase voltage as EL is equal to root 3 times EP. Similarly, if I want to derive what is the relationship between the line current as well as phase current, since it is a star connected system, so we have seen the star connected system represented it in this manner. So I am having three distinct phases which are connected in Y form. So we are having the lines like this, and I had represented the currents, say IR, this as IY, and this as the current, that is IB. So this was the neutral point which we have used for making a common connection, so represented as N. So in this, if you see, IR current is entering. So this is the individual line R, line Y and line B. So we have the current IR, which is called as a line current. So if you see this particular phase, even the current which is going to flow from this particular line is going to enter into this particular R phase. Similarly, it is having another connection given to the neutral point. So it is just behaving like your series combination, which states that the current will remain same. Similarly, if I consider the Y line, so line current IY, the same line current IY will be flowing through this particular Y phase, and IB also, the same IB line current will flow through this particular phase, which is in turn connected to the neutral point. So it is not having any division of current, or it is not going to find any node where the current is getting splitted. So the line current as well as the phase current will be same in case of your star connected system. So I know what is the relationship between the line current and phase voltage, as well as line current and phase current, also the line voltage as well as the phase voltage. So when I am having the relationship in regard with the voltage as well as current, next thing is I can find out what will be the equation for power. So in general, you know, the equation for power, when it is considered in terms of a single phase supply, it is equal to VI into power factor, that is cos phi. But now here we are concentrating upon a three-phase system, so I have to multiply it with 3. For single phase means it is holding good with the equation of V, just Vi cos phi, but now it is a three-phase system, so it has to be multiplied by a factor of 3. So instead of V, I am having the phase voltage now EP. Instead of I am having a phase current represented as IP. So it is 3 into EP IP cos phi. From the derivation, we know what is this EP as well as IP. So we have EL given as root 3 EP. So I can write EP as EL divided by root 3. So instead of EP, if I substitute it as EL by root 3, IP and IL, both the line as well as the phase current for a star connected system, it is same. So it is represented as IL. IP value, I have substituted it as IL. So it is in terms of line values. This is the relationship in terms of phase values. So it is root 3. Here if you see, it is 3 into EL by root 3 into IL into cos phi. So 3 can be written as root 3 multiplied with the root 3. So one of the root 3 terms will get cancelled. So I can just write this particular 3 value as root 3 multiplied with root 3. So this root 3 multiplied with root 3 is nothing but equal to 3. So one of the root 3 terms will get cancelled out with the denominator part, and we will remain with the final equation, which is given like this. So root 3 EL IL cos phi. So this is the total power output what we can calculate for a three-phase system, that is star connected system. Suppose if I want to calculate what is the apparent power, once again considering the three-phase system itself, if I want to calculate what is the apparent power, it is thrice the apparent power per phase. So apparent power per phase means it won't be having this cos phi terms. So ignoring the cos phi term, it is called as an apparent power. So it is 3 multiplied with EP into IP. Just 3 into EP into IP will give us the apparent power of a three-phase star connected system. So EP is nothing but EL divided by root 3, and IP value is equal to IL itself. So if I substitute once again 3 as equal to root 3 multiplied by root 3, one of the root 3 terms will get cancelled out, and you are going to remain with the expression for an apparent power of a three-phase star connected system, something like this, that is root 3 times EL IL. So we have seen how to derive an expression or how to find out the relationship between the line voltage as well as phase voltage. Along with that, the line current as well as the phase current relationship for a star connected system, that is three-phase star connected system. Along with that, we have also seen how to derive the expression for the total power output as well as the apparent power for a three-phase star connected system. Hope you understood this derivation. Thank you for listening.